Good morning, everyone, and welcome. I am Helen Harrison of the Northwest Eco Building Guild. I'm a committee member of the Slam and Summit. Shawn's going to hang out with us during this intro. It's okay, Shawn.
Or not.
And I have Ellie with me. She's going to aid the session in session support. So if you have any questions or issues technology-wise, you can find her in the chat section and send her a private message, and she can help you out. And just a quick note for viewing slides better, you can minimize your chat screen to the top right corner by selecting that green arrow pointing right. And you can also make either of the screens or any of the screens that you see in front of you bigger by selecting the 4 arrows in the top right corner of the image. I would like to take a moment to honor the land that we currently occupy. On behalf of the Northwest Eco Building Guild, we acknowledge that we are all on the traditional land of the first people of this region. We honor with gratitude the land itself and thank the tribal people who have been faithful stewards of the land, water, and ancient history of life. Here in Seattle, where I am, we are on the land of the Duwamish. Peace, dignity, equality on a healthy planet. This is from the United Nations. It's simply stated, but deeply resonates with our committee as we think about you and the need in our community at this moment. We believe that you all are part of a group of people to set an example for how to support one another and move through this time together to arrive in a better place. I'd like to thank our sponsors. Our sustaining sponsors for this event are King County Green Tools, Dunn Lumber, and Faros Creative. We've got some supporting sponsors as well, many supporting sponsors, too many to mention right now. We've also got some contributing sponsors that we'd like to thank. All of our sponsors make this event possible to share the information we've got for you today. Before we get started, I do want to take a few more housekeeping notes for you. When we finish our presentation, you'll see a show floor like this in the picture on your screen. I think most of you are probably familiar with using Remo by now, but if not, you can ask someone at your table for help. If something really doesn't seem right and you've got quite a few issues, try moving to another table or leaving the meeting and coming back in. If you have camera and mic issues, you can see the 3 bars in the upper left-hand corner of your screen that will open up a menu for you to test your microphone and camera. And you can also find help from one of your event hosts, which is anyone at the table that has a yellow star, like the image enlarged on your right. I am excited today to introduce our speakers for this session. We've got Shawn, Oram, and Paul Kintner from Ecotop. Shawn's focus is on energy efficiency and its relationship to building design. Shawn assisted in creating the guidelines for the design for off approach to creating low energy buildings and can often be found diving into the latest emerging technologies. Paul is a researcher and engineer at Ecotop with experience in thermodynamics and heat transfer modeling. He's been instrumental in delivering the new Ecosizer, an innovative tool used to help design heat pump water heating systems, which is what we will all learn about during this session. Paul and Shawn, you can come up on stage by turning your microphone and cameras on, and then take it away.
All right, here we are. Thanks, Helen.
Yeah, thanks, Helen. Thanks, Ellie.
Let's see, so do we have the screen here? All right, let's get started.
Yeah.
All right. Hi, Shawn Oram with Ecotop. I am the Director of Design and Engineering, and we're here to talk today about some of the work that we've been doing focused on kind of a new movement that's happening around central heat pump water heating. I've also got Paul Kintner here, who's sort of chief architect and visionary behind the new Ecosizer tool. So we're going to also follow that. And then we're going to show you kind of an exciting sand and skid. So first slide here is really focused on, this presentation will be focused on heat pump water heating. And the first question that typically comes up is, why is this needed? We've got central gas systems that the market has been, has responded well to. And the reason we need to do this is to meet Washington State climate goals to be carbon neutral by 2045. And so the other reason is to also meet our energy use reduction goals of 60 to 70% over 2006 levels. And the reason that we're doing this is to reduce our carbon emissions and also to free up grid capacity as we take on electrification. And electrification is simply transferring our vehicles to electric vehicles, transferring all of our thermal needs that are currently done with natural gas over to heat pumps. And that is the direction that the West Coast and probably the rest of the nation is going to follow as we start our transformation. The next piece is we'll focus a little bit on, or actually quite a bit, to introduce a new sizing tool called Ecosizer. This is designed specifically around central heat pump water heating systems. It's a really exciting tool. It's very powerful. After you get through this learning and understand how to use this tool, there will be really not a lot of questions left in terms of the sizing. And that's been one big hurdle as industry has tried to take on the heat pump water heating scope. Thirdly, we'll discuss a bit of some packages built around Sandin. So this would be a Sandin skid. This is a rooftop package that's being assembled with the goal of trying to reduce a lot of the risk for the installers. It reduces cost because the idea is it's plug and play. And from a utility standpoint and from an incentive standpoint, the idea with having the skid is to allow for repeatable installations and predictive performance. And so this is really what the utilities will grab onto. It's essentially trying to widgetize our central heat pump water heating systems so then they can be incentivized. Next. As I mentioned in that previous slide, one of the primary goals for both the energy code changes that are happening as well as kind of regionally is to attack central hot water, which is typically done with gas. And so naturally, we do have to electrify our buildings. And I'm showing over to the right a kind of a graph of if we had 130 unit apartment, and we said, oh, let's electrify our buildings. Everyone puts in an electric water heater inside of their units. We can see that what we're going to do is result in a really high peak load. And so the blue line is sort of electric tanks in units with the diversity sort of modeled against the typical flow profile in a multifamily building. And on the bottom, we can see what the grid sees, or the input energy for a heat pump system. So this is a peak difference of about 310 kW versus about 18. And that's the real power and the value and why we need to go to central heat pump water heating, is that it's the best, easiest way to accomplish both of our goals, both the carbon reduction as well as the energy use reduction. Next. And on this quest, as we start to look at transforming the domestic hot water market into electric heat pumps or electric heaters, over to the right kind of shows if you do this switch today, these are kind of what you're looking at. And so gas right now, fossil gas, fracked gas remains cheap, and that's their position in the market. The central systems are really, for most multifamily buildings, this is sort of the least cost, and the industry has kind of accepted that as that central. And, the heat pumps, electricity does cost more than gas. And so if you look at electric tanks in the unit, you're going to essentially double the operating costs. So you have to be careful in that one. It's also, like I showed before, huge peak load. But the two to the right, RCC and CO2, those are two different types of heat pump, central heat pump systems. And so we can see those costs are comparable or better. And so that's another reason from an operating cost standpoint that the central heat pump is an important system. Next. And then the same goes with lower emissions. So this is using Seattle City Lights grid. We can see gas emissions, 135,000 pounds of CO2 per year for that same 130 unit. And then we can see what happens as we switch to electric. Keep in mind, Seattle City Light is a carbon neutral utility. And so we can see sort of the emissions down below. But one important part is it's a factor of 20 reduction, and that's a huge step towards the state goals. Next. So I mentioned some of the changes coming in the energy code. One of the big changes that happened for all R2 construction, so this would be multifamily and hotels, so all R2 sort of construction, heat pump water heating will be required by next year, so 2020, January 2022. The heat pump water heating with the CO2 refrigerant will also net 5 C406 points in the new energy code where we've got the C406 points. So there's a lot of focus on trying to transform the market. And so this would be a carrot sort of in the market offering the 5 C406 points. And kind of the bigger picture, there's a huge effort that is happening. Ecotop is sort of leading the way with California, and so that's part of what you'll see with the Ecosizer. But the Advanced Water Heating Initiative is really a group that's got multiple utilities involved. It's really focused on market transformation. It's likely all focused around California because they're taking this on in giant steps. And so there's a lot of work happening behind the scenes now to get the market ready, which is what this group is focused on, getting the market ready and the designers. And so the tool that Paul will present later is that it is a tool to help the designers, because that was one of the big hurdles, is how do we do these central heat pump water heaters. Next.
Yeah. Thanks, Shawn.
All right. Yeah. There's Paul.
So as he said, this was funded primarily through California utilities. So the Ecosizer is this great development tool that you can use to help size these central multifamily heat pump water heating systems. And you can find it here at ecosizer.ecotope.com. And this web domain's plastered all over, so you'll have lots of chances to see it if you forget. So this is kind of in motivation to help designers size these systems, because they're new and they operate very differently than boiler systems. A lot of the older methods were just guess, and if you vastly oversize a boiler, you're going to end up with a system that's fine. The boiler doesn't care. You'll have a lot of extra heat capacity, and no one's ever going to notice. But if you do this with heat pumps, you can end up ruining the heat pump, right? You can end up short cycling it and drawing in hot water, which heat pumps don't usually like. And so the older method, besides guessing, would have been the Ashrae method if people actually followed it. But this was also a little dated and focused predominantly around boiler systems and instantaneous systems. And so we at Ecotop have actually been using this method in sizing systems between 2 to 3 hours. And so what that means is you're looking at the peak 2 to 3 hour period throughout the year. So that would be kind of be the gray area in this graph here. And you say, I'm just going to shove all of this in storage. But in reality, you can actually generate hot water at the same time, right? So if you're not having an instantaneous system, you might want to factor that in. So I ask you this question: is it giving the right size, but predominantly for the wrong reasons? And so one of the main goals of this Ecosizer tool is to help standardize the method so that everyone can use it. And if you're going to a manufacturer to tell you how much heat pump capacity and how much volume you're going to need in your system, it's hopefully will help remove some of the mystery behind getting that size. And I know at Ecotop we've had to compete with bids with some of the manufacturers as well. And we can't necessarily say how even they're getting their system sizes, but we can at least back up our own sizing system. Also, we really need to be focused on standardizing the schematics for these central domestic hot water systems, and we'll get to those later. But sizing these systems tends to go hand in hand with the schematics. And also, the last goal of this Ecosizer tool is to educate users, right? This is an entirely new system, it's a new tool, and change is kind of hard, right? So we want to help encourage people and help make this change to these new systems easy. And so when we're sizing these systems, we're looking at predominantly two separate domestic hot water loads, right? The primary heating, this is what people are using when they turn their taps on and they take their shower. It's the load that takes to get your incoming mains up to the hot water temperature. Yeah, right, it's making cold water hot. And this is what heat pumps are good at, especially these CO2 Sandin heat pumps. And then there's the temperature maintenance load. That's the reheating warm water to hot water so that everybody in the apartment building can get hot water in a timely fashion. The person that's farthest away from the plant doesn't have to wait 10 minutes after they turn on their taps to get hot water. And together, these in Seattle, they make up about a quarter of the total building load in multifamily buildings, which is significant. But this temperature maintenance part takes up about 10% of that total load, and it can range from anywhere from 30 to 50% of the domestic hot water load. So it's a large load, and it's mostly just dumping heat into the crawl space or between the walls of the building. And so it's mostly just wasted energy. So we should be taking measures to reduce that load. So specifically how we get the domestic hot water load is we think about how many people are in the building and how much water they use. So the data in the building comes from about 4 years of monitored data from one building. It's a 118 unit building that Ecotop designed and monitored. And this is kind of our design building, right? We've monitored a bunch of buildings around the area, and this one shows up time and time again to be the highest use building. And so we look at about the 98th percentile, 95th percentile, which comes out to be about 25 gallons per day per person. So that's the number we're using. And then we want to have users tell us how many people are in the building. And there'll be a few ways that they can do that, which we'll get into later. And then we look at this design day load shape, right? This is the peakiest day. During the hours from about 6 to 10, right? So that 4-hour period, users are using more hot water than they are at any other time during the year. And then this day comes out to be about the 95th percentile day of the year as well. So it's using about 25 gallons per day. And then the second part is a temperature maintenance load, right? This is the other half of what we're designing to. And the difficulty in designing this part is that it's really hard to predict what that load is going to be in a new building, right? If you're in a retrofit, you can just go out and measure it. It's not that hard. But we did a survey of about 45 buildings, right? And the variance here ranged from about 40 watts per unit to over 500 watts per unit. And so there's a lot of difficulty in designing these systems and making sure they're built the way they're designed. The median value here was about 100 watts per unit, and this is what we recommend designers use for new buildings. If it ends up being a lot higher, you should really think about how you designed your building and what went into it. Typically in Seattle, we see about 50 to 100 watts. And this is great. It's acceptable. If you can get down to 50 watts, you can really start cutting down your energy use. It's great. Then the other thing here is that we have a lot of trouble predicting what this value will be beforehand, right? So what you see on the graph here is 3 buildings Ecitope did built. And the blue here is a theoretical calculation. This is just a pipe heat loss calculation. We have so much pipe, this is the diameter, and we expect this to be the temperature gradient across the pipe. So this is how much heat we're going to lose. And we did decently in one building predicting this, but these other buildings, we're off by over 100%. And so one of the big factors with these buildings is having insulated pipe clamps and pipe hangers. So that's part of the story there, is that you do have to insulate every single part of the pipe, especially if it's bridged to the building. And so the first system we're going to talk about is a parallel loop tank, and this takes these 2 loads and separates it out into essentially 2 separate systems: the primary system on the left and the parallel loop tank system on the right. And so on the left, we have our single pass heat pump water heaters and our primary storage volume. And this just heats that domestic hot water load. It's just heating water from the city up to the storage temperature so occupants can use it at their taps. And then the parallel loop tank, we're using a multi-pass heat pump water heater, which essentially takes the water from the bottom of the tank and is going to add 10 degrees or so at each step and insert it back in the top. And so this system sees just the temperature maintenance load. And so we've completely separated the 2 parts out here, and it works well. But you're also buying multiple heat pumps for this system, so the cost can go up. Here's an example of one of these systems in practice. On the top here, you can see this is the parallel loop tank. It's very large. It also has an electric backup in it. In case one of the heat pumps goes down, it can still provide hot water to the occupants. This large thing here is the mixing valve. On the bottom left, we have a bank of storage here. I think these are all 500-gallon tanks. And they're plumbed here in series. So the top of one goes to the bottom of the next one, and that goes all the way down the train like that. And then in the center, we have one of our Colmac heat pump water heaters here. And top right, it's your expansion tank. And there's another backup resistance element here. This is a small tank, but I think it's full backup in the resistance element here. So it's pretty much an instantaneous heater. And then on bottom, we have our recirculation pump. So the system all comes together and works beautifully in this situation. The other system we think about designing is a swing tank. This one gets a little more complicated, but you can see on the left, we still have our single pass heat pump water heaters, which take in the city water and spit out the water at set point. And this feeds to our swing tank, which is essentially used to just capture that temperature maintenance load. And so the temperature maintenance load comes back to the swing tank, which is actually heated by the primary storage system when there's hot water draws, right? And so we suspect we can get about 50 watts per apartment at best on kind of your average building, shifted from the swing tank to the single pass heat pump water heaters. And so we do expect that the resistance element will run, right? It's going to be hard to completely eliminate that unless you've got a system that's down at like 20 watts per apartment, which would be fabulous. But otherwise, the temperature maintenance load just tends to be too large to really shift all of that load onto the primary system. And so the next slide here is going to show us a swing tank system we've built. This is about a 60-watt apartment, and here we're using 4 stand-ins, which you can see here on the left. And And then on the center right, we have this the room where we keep all of the storage tanks, right? So the stand-ins sit outside because it can operate down to 5F at a constant heating capacity, which is really nice, really simple for designing with. And so there's 3 storage tanks here, and then we have the large swing tank, which also has an electric resistance element in it. And then here's the recirculation pump on top right. So the systems work great. The only risk with this system seems to be that you can take out your heat pumps during ice storms. If they're outside, things can fall on them essentially. Then let me get into the actual Ecosizer method. So as I discussed before, the Ashrae methodology would size your system to about 2 or 3 hours of your peak system, and you're going to put all of that in storage. That works well, but we can define a better system, right? If we have the hot water demand, this is what the occupants are using, right? It's shown here in blue. We can also define a hot water generation rate, how much hot water the heat pump water heaters are going to produce per hour. And we usually size this so that the heat pumps can produce the entire day's worth of hot water in 16 hours. And so that defines some hot water generation rate. Here in this example, it's 100 gallons per hour, simple. And so if we can generate through this peak, right, then you only need the difference between the orange line and the blue line. So the area under the curve, that's the green, right? We can define this part as the running volume of primary storage, and the plots on bottom shows what happens at the 6 a.m. peak, which is the blue line in the green area. But we also, in the sizing methodology, just for being complete, we're going to check every kind of peak period where the hot water demand exceeds the generation rate. And so the orange line is a peak in the evening. And this volume is just less than the morning peak. So we're going to size to the morning peak. And as I said, we're going to use that green area, and we're going to find this as the running volume. So the running volume is, we know the tank's going to be running. It's beyond the Aquasat. So the whole time that the tank level is in this running volume, the heat pump water heaters are going to be trying to catch up and fill the tank. And so the other user input, which is a major factor here, is this Aquasap fraction. And that's the distance, or the volume that you have to lose in your primary storage to trigger the heat pump water heaters to turn on. So this big T is just your Aquastat. And so the total storage volume is essentially just the running volume multiplied by or divided by the Aquastat fraction. And then for the parallel tank, this is fairly easy, right? It just sees one load. It just sees that constant temperature maintenance load for the whole year. So we're just designing this system to cycle on and cycle off. So we essentially define the deadband, the set point, and when that's going to turn on. And then we're looking at a period that we want to be greater than 20 minutes for the heat pump to run on for. And so and that's just to prevent short cycling. And so the users tell us how the safety factor they want and how long the system should be off for, and we'll check for that short cycling. The swing tank is a lot more fun, right? Because now we have some dynamic interaction from the primary system heating up the swing tank when there's hot water draws. And so we looked at some simulations of this, and you can see the results on the top plot here. This is the % annual energy reduction that we get in a swing tank from oversizing it from 80 gallons. So if we think of 80 gallons as a baseline, how much energy can we reduce in the swing tank when we oversize it to 120 gallons or 500 gallons, right? And so it turns out when you're at 100 watts per apartment, which is kind of our median value, you don't really see much of a change when you're oversizing, right? And this becomes the temperature maintenance load just dominates the system. And so you end up, if you have an 80-gallon tank, if you increase that to 700 gallons, you only reduce the energy load about 4%. So there's not a huge benefit in doing that. But if you're able to get your system down to 50 watts per apartment, and you increase it from 80 gallons to 700, you're up by like 24%. So there's a lot more benefit to increasing your swing tank volume at lower loads. But at higher loads, it doesn't matter so much. And going in APRE, no one really knows what it's going to be. We can kind of only assume it's going to be the average. So we come up with a system for sizing the swing tank just based on the number of apartments, right? You can get away with a smaller swing tank even when you're at 100 apartments or so. But you really can start to see a benefit in sizing up at larger apartment sizes. California also has a executive order prescribing swing tank methods, or the swing tank schematic, and allowing it to be used in code. The Title 24 has its own sizing methods, which were done sort of without modeling. They're a little dated at this point. Granted, they're only go back to December of last year. So these are likely to be updated soon, but the values are given here just to keep things consistent. We're also sizing for load shifting. And this is this example, right? We're thinking about the same methodology, but now we're prescribing blocks of time where we won't be generating hot water. And so we're using that same methodology, but the hot water generation rate goes to 0, which you can see on the bottom 2 plots here. And so we've got 3 examples: no load shifting, evening load shifting, and evening and morning load shifting. And so if you're doing just evening load shifting, you can get away with the same heating capacity because you're not really blocking that much time off, but you need to increase your storage volume because now the area under the curve in the evening from about 1700 to 2100 is a lot greater than the area you saw when you were generating hot water during the morning period. However, if you're shifting to morning and evening loads shift, then you need to kind of both increase your heating capacity and storage volume to meet these new loads. So let's get into the Ecosizer, right? So when you load up ecosizer.ecotope.com, which I encourage you to do, you see this great landing page. It's got some instructions on how to use the tool and some motivational words to get you excited about it. And the first thing that the tool is going to ask you to do is to size the number of apartments and the number of people in the buildings. And if you just know the number of apartments and people, you can just input those straight up. But if you don't, you know how many apartments are there, but you're not really sure how many people are going to be in the apartments, you can use this other method, which is just a toggle, and input your number of apartments. And there's a few options for assuming the occupancy rate. So there's, for studios, maybe there's 1.49 people. We provide an Ashrae market rate number as well as a low number. And if you're worried about where these numbers come from, you can always click the question mark, which will provide you with some text there and should provide sources. There's also California numbers, one's provided that matches CBEC Res, which is their building energy modeling software used for code compliance. as well as a California low income estimate, which tends to be very high, but also has been shown to be accurate for low income buildings in California. The Ecotope market rate with low flow fixtures is our estimate of how many gallons per day people are using. And this comes from that 118 unit building we saw before. There's also peak gallons per day provided by Ashrae. The Ashrae low is 20 and the Ashrae medium is 49. I remind you that the Ashrae numbers are from 1990s and the 49 is probably extremely dated. This is before low flow fixtures, anything like that. But you can also go through and set the peak gallons per day by the apartment size. So that's a neat feature. The next thing the tool is going to ask you to do is think about the water temperatures, right? So the design cold water temperature. What's the coldest temperature that the city is going to provide you? The supply temperature, what the occupants are using, and this is typically 120 to 125. And then the hot storage. This is what the heat pumps are putting out in your primary system. So 149 would be what you use for stand-in systems. And then again, here we see the Aquasap Fraction. It's usually around 40%. You might, once you know how many tanks you want, and which tanks you're using, you might go and input where the Aquastat is actually going to be. So if I'm using 2 tanks and they're both at 40%, then in reality, if I put it in the first tank, that's 40% of that tank, but that's only half of the total tanks. It might be more like at 30%. So I could lower this value. And it's going to check that with this, that we're not short cycling as well. And then you get to choose which sort of temperature maintenance system you want to use, whether that's the swing tank, where the primary storage is plumbed directly to the swing tank, or the parallel loop tank, when that primary storage is piped straight to the mixing valve and ignores the temperature maintenance losses, or the primary with no recirculation, right? So you don't have a temperature maintenance load that you're trying to design to. Or maybe you want to just use trace heat and put some trace heaters on your distribution piping to keep it hot. The advanced schematic options you can click, and this will help you design your temperature maintenance load, right? So we default to 100 watts per apartment, which you can go and change if you know. If it's a retrofit, and you can go about and measure it, or maybe you have a good estimate of what your return temperature is, and you know what the flow rate is going to be. You can input these, and we can calculate that heat loss for you. And then there's a temperature maintenance system safety factor. And this is what's really used to size the swing tank heating resistance element and the parallel loop tank multi-pass heat pump water heater, right? So this here we default to 1.75 because this is most of the buildings we see. I think the 75th percentile is actually 175. So we hope all new buildings should be at least below that value. And so you should be able to meet the temperature maintenance load and heat up the swing tank or parallel loop tank. And the last section here I want to go over is the load shift section. This we offer 2 periods that you can size to an evening or a morning, or maybe you want to size so for both evening and morning and only heat when there's solar. This is a great way you can play around with these sliders and really size to whatever load shift period you want. And then we have this percent of load shift captured. And this is predominantly because getting all of the days in load shift is a lot of storage, right? You might have a 60-unit building that you could get away with having 400 gallons of storage, for example. But now if you want to load shift every single day, you might have to increase that storage 3-fold, which is a lot more. And that's a huge step to ask designers and engineers to do, just to kind of get this load shift working. So what we provide here is just a way to say, hey, maybe I just want to do 95% of days, or do the median day. And the median day ends up being about 70% of the hot water load, of the peak hot water load, I should say. And so once you kind of do all these, input all these systems that you want to look at, you can click this nice size it button, and it'll give you these results out, right? So you get a nice sizing curve. So we're looking at the primary tank volume versus at the storage temperature versus the primary heating capacity. So volume versus heat pump capacity, right? And then we provide this recommended value, which is sized at 16 watts per apartment, or sorry, 16 hours of runtime per day for your heat pump water heaters. And then we give you the recommended swing tank volume and element size, as well as the California Title 24 swing tank volume for users that just might be there. But you can also play with this slider to size different systems, right? Like, no one's ever going to actually have an exact heating capacity of 150 kilobtu's per hour, but maybe you can get to 124 in your system. So you can drag your system down for that heating capacity and see what the minimum storage volume would be for that. Or vice versa, maybe you already have tanks there, and you could say, hey, I have 130 gallons, right? Or 1,300 gallons. So you can slide the slider down there and see what your minimum heating capacity would be. There's also this option to save results to PDF. So it'll just print you out results with all of your inputs and your outputs and your selected system from this sizer, from the sliding tool. So you can recreate all of those results. Yeah, so thanks a lot, and I will pass it back over to Shawn.
All right, thanks, Paul. So again, that's the Ecosizer, and this is free for everyone to use. Ecotop is a mission-based company, and so this is one of the key pieces to our company is to help advance everyone towards carbon neutral building. So this is the first of many tools to come. So thanks for Paul and his team of developers, programmers for putting that together. So the other piece and kind of the segue from there is to kind of show maybe some examples of some cold climate heat pumps, and also show you a plug and play option that we are working on for a project down in California. So this next slide is really kind of highlighting the Sandin product. This is a CO2 based refrigerant. This is a very popular, a nice product. There are some more CO2 products that are coming into the market, mainly out of Japan and Europe. And so the movement to do central hot water with single pass CO2 is from a world perspective. There's a lot of focus on that, and so they're really kind of waiting for the markets. But they're really great heat pumps. Next. So the product that we're going to talk about is kind of it's a packaged Sandin based system, and we're focusing on the Sandin now because that's a product that we can actually buy. There's other CO2 that are not quite ready for the market. We've got some pilot studies going with a couple other products, and there's a couple other systems, but this one's going to focus on kind of the modular Sandin setup. So we did a lot of the lab testing around the Sandin. You can find this stuff online, but you can kind of see some of the capacity and COP relationships here. I won't get into this. Paul, next. As Paul mentioned, a single pass design. So this is a design that we've been working on. We've got it in play in a project in Capitol Hill. It's running about a COP 3.0 seasonal. So that's really great. And again, as Paul mentioned, we got to get our temperature maintenance loads, our recirc loads down below 50 watts an apartment. It's really important. Next. So this then starts to develop, and we've worked with Sandon. We've had some funding from utilities to help us kind of get organized around kind of more plug and play packages. And so if you look at sort of number of occupants served, this is kind of an example of how if you go to a Sandon dealer, Small Planet or other reps or dealers, they'll start to put these systems together based on how many occupants you served. And so really having this kind of modular arrangement will really help, I think, to bring the cost down and the complexity, and really to get us away from all of the risk padding that's happening in a lot of the bids right now. We really got to cut through this kind of early phase pricing to really transform this market and get ready for what's inevitably going to be every building's going to have a heat pump water heater. Next.
If I could interrupt, can I interrupt for just a second? It looks like some people are having trouble viewing the slides in full screen. So Paul, if you could turn off your video camera, then people will be able to see them a little better.
Okay, thank you. And then with these systems and packages, we're kind of envisioning there's a set of instructions, and these systems can be kind of site assembled. They can also be pre-assembled. Next. This is a particular project that we're working on down in Menlo Park. It's in the Bay Area, California. If you're aware or not, there are about 30 jurisdictions in California that have outright banned gas for new construction projects. And so this has left the market in a little bit of a scramble, but the manufacturers and the designers are stepping up. The investment in the tools, which Paul showed you, the Ecosizer. These all kind of came out of what does the market need to really transform this? Well, this particular project here is utilizing a factory-built plug-and-play sand and skid. This will serve about 100 people. We've got these mounted on top of roofs, and so the idea is we bring these. These are fully functionally ready to go plants, and we crane them up to the building and drop them onto pads that are pre-configured. This is a really nice option because of the sequencing and staging and building up multiple plants. These will serve 100. And so we've got these on about 800 units worth of multifamily buildings down there. So we've got 16 of these skid pairs going into this project. This skid pair will have a full M&V system. The idea is it's plug and play. You drop it in, you connect to the water, you connect to the electrical, and then the internet connection. So those are kind of your 5 major connections. It's all factory tested. It's ready to go. So this is one vision that the utilities and Ecotop have been centering around, is trying to get these systems into more packages. This one's designed mostly around California climates. Most of the water heating plants are on the roofs down there. Up here in the north end, we've got to modify this a little bit because we freeze a lot more often. And so we've got to have our tanks in heated space is kind of the recommendation. But these tanks are they've got an advanced and a basic controller that'll be standard with kind of the sand and multifamily package, and they are load shift capable. And so there will be signals that get sent to these plants from utilities to tell us to shed up or to load up or shed down. And those are probably new terminology for Washington because we don't have time of use rates, but it's coming. The reason it's coming is because a lot of different PUDs and electrical utilities are running out of power on the coldest Monday morning in the wintertime. And so as we start to electrify cars and space heat, that's only going to get worse. And so we've got to try to move load out of that morning peak, because that's what requires the utilities and the whole grid to upsize, to add more capacity. So that's really kind of the next move in our local grid, is sort of making room for electrification. That's it. Next. This is an example of that Menlo Park project. So this is 400 people, 250 units, 5/1. we've got 4 rooftop sand implants. It's a little hard to see, but the idea is we'll drop 4 of these into this project, and we've got 4 small loops within the project. We plan to have this installed in about a year, so we're still working on getting the fab set up and getting it all kind of dialed in. But we're excited about this product. It really kind of shows, it essentially tries to widgetize these central heat pump systems, similar to how single-family integrated heat pump water heaters work. And once we can get to that point, then the utilities can now provide incentives. And so that's really the drive for that. Next. And that's the end. Are there any questions?
All right,
Okay.
a couple of questions, Shawn.
Okay.
From Tom Balderston, how do very low flow fixture specifications, say 0.5 gallon per minute lavs and 1.3 gallon per minute showers, affect this sizing?
It has a direct effect because the tool that's there really allows for customized entries, and so the lower flow stuff's probably going to result in what you sort of need out of that fixture selection is you need kind of a gallons per day, so gallons of hot per day, and there are calculators that can kind of estimate that. But it's hard when you're designing the building to know how much water someone's going to use. And so you have to this is up to the designer, how conservative do they want to be? How conservative not? We use a lot of data from past projects just because predicting a lot of this stuff, predicting human behavior is pretty hard. But no, I think that, if you've got gallon per day projects, but those particular specs, then I would use those. But generally 15 to 25 gallons of hot a day is pretty typical. If you're on a low flow, then you probably want to use something closer to 18 or so. But you can fully customize that. It's just, you've got to be comfortable and make sure that you're right. It doesn't hurt you to oversize a little bit on a gallon per day. It's kind of a safety factor, but you can play around with it and kind of see what's comfortable. So that's a long answer to that.
Question here. This one's for just single family units, wanting to know, how is a system like this better than a solar water heater system?
That's a great question. Solar PV and solar thermal, those are kind of the two renewable. If you look outside today, I'm looking outside, I don't see any sunshine. So I don't know how your solar system is going to work. And I think this is kind of the case for the next about 6 months. So how do they compare? Cost effective wise, you're going to get way more savings out of a central heat pump, significantly more savings, significantly more peak load reduction. But I would say that compared to electric in tanks, a central heat pump system, because of the enormous savings, it's probably a 2 to 3 year payback. You can't say that for solar PV or solar thermal.
Similar question from Christina. How do on-demand hot water heaters compare to these kind of heat pumps?
In terms of the user experience, if they're sized right, there's no difference, right? You turn the tap on and you get your water. From the grid standpoint and what the grid sees, it's an enormous difference. So on demand, there's electric and there's gas. Well, moving forward, it's going to be a lot harder to spec gas anything, just because of the climate goals of the state. But there's no difference in the user experience, and there is a big difference. That first graph I showed, the more central you make a water heating system, the lower your total building energy draw is. So there's a bunch of different kind of criteria here, but you really try to get everything as central as possible, because that's how you get the lowest draw. And we also need to be thinking about load shift because it is coming. SNOPUD's got a pilot project now for time of use rates. Tacoma's talking about it. Seattle's talking about it. So this is coming. It's coming quick. But yeah, I think going back to the question, this is I don't think there's any difference from the user side. It's really just on the grid side and your fuel side.
Build on the last low flow question with low flow fixtures, or will low flow fixtures create any problems like they sometimes do in single family residential systems in not being a high enough demand to get good hot water?
Yeah, absolutely. You know, the way to really, you know, sort of attack a central heat pump or a central hot water system is you really have to start at your, you know, what's called a time to tap spec. And so you kind of have to work backwards. We tend to, as designers, we work the other way. We start at the plant and we go out, but you actually have to start at the units and go back. And the goal, you know, is obviously to get your distribution losses down and such. But one thing to keep in mind is if you've got big pipes, you know, the way a central system works is you've got kind of the moving water parts that are more in the central locations in a building. And then you've got little manifolds that go to each apartment. And from those manifolds, if you've got big pipes feeding low flow fixtures, it's going to take a long time to clear out all that, you know, warm, you know, room temperature water before the hot comes flowing in. So if you've got low flow fixtures, I would recommend that you size your piping relative to that, and you look at the time to tap spec on there. So in summary, this can be designed out, but if you put a 1/2 inch line feeding a 1 GPM lav, it's going to take you, you know, several minutes to get the hot water. So you have to kind of, you know, you have to look at the system as a kind of holistically, I guess.
Question here is, who currently sells the plug and play kit in North America? And I think you said that's actually something that you're working on now. Sounds like maybe it doesn't exist, or it exists somewhere else.
Yeah, no, that's a great question. It doesn't exist yet. This is kind of a sneak peek of what we're working on. So we are going to have it fabbed up. We're looking at several different fabricators right now, and you know, we'll see kind of what evolves out of that. But this first phase is still in this kind of pilot phase. We've got some funding to kind of support it, to meter it, to really understand it. But yeah, I would say that, you know, if you're looking for kind of packages now, we don't have plug and play, but I know that Sandin and Colmac and a couple other rep firms, they've got now pretty good capability. We've been working with both of those, you know, with both Sandin and Colmac on that, so trying to get them ready.
Got it. Next question is, it seems the Ecosizer has 3 methods: parallel tank, swing tank, and load shifting. Can you speak to how to select the best sizing method and what considerations you take with each method?
Yeah, you know, as Paul kind of showed, the 3 different methods really come into play. I mean, they really are a function of what you plan to do for temperature maintenance. And you know, if you're approaching an existing problem, so an existing building, you know, we can go measure the temperature maintenance, flow and delta T across the building, and then we'll understand, you know, what the losses are. But in new construction, as Paul mentioned, it's actually pretty hard to kind of predict this. And so, you know, I would say that it really goes into I think the size of the building, but generally speaking, if you've got a small building, you know, 100, and, you know, serving about 100 people, 60 units or so, then the swing tank is definitely, I would point you to that direction because it's just going to be less cost. So I would say up to, you know, I've got a project now, it's got 2 Sandin plants in it. And that's 110 units low income. So there's a lot of occupants in there, 250, and that's 2 Sandin plants with the swing tank. So it really kind of gets down to how you want to design it. If you've got a bigger building, it's likely going to have a bigger temperature maintenance load. And so then you'd want to move to more parallel just because the temperature maintenance load is so hard, is so much bigger. And then the case for no circulation would be getting the hot water plants really close to the end use. So this would be like an example would be floor to floor, or splitting a water heater, at the end of a double loaded corridor into 4 units, and then just doing small piping and running out, from that tank just to 4 separate units. So we've seen that kind of design as well, kind of emerging. So I think those are kind of the 3 examples of when to use.
Just to add on to that too, which kind of method or schematic you're selecting also is a product of your heat pumps, right? So the Sandins, the default output, excuse me, the default output temperature for these systems is going to be 150, which is great for the swing tank because you're adding a lot of extra energy into that swing tank. But if you've got one of these Colmac or Nile systems, you have a lower COP when you're outputting higher output temperatures. So if you're outputting 150, it's going to take a COP heat hit to the system. So you might choose the parallel tank where, excuse me, you might choose a parallel tank where the temperature of the primary system doesn't affect how much recovery you have for the temperature. Yeah.
Got it. We've got one more. Thank you. Could each unit have a pony tank? How would that affect the system? That question's from Catherine. Not really sure. Maybe you understand what she's intending to ask.
A pony tank. Is that like, I guess, is that like having a tankless water heater and then having a little auxiliary tank to run your recirc through or out of? I'm not familiar with the term pony tank, or maybe what the context is.
Hey, Catherine, I invited you to join us on the stage. Do you want to maybe clarify that for Shawn and Paul? And Paul, would you like to turn your camera back on?
Oh, yeah.
Yeah, for each unit to have its own little recirculate little tank, little storage tank. But if they did that, how would that affect the whole system? So that way they could have their hot water. They could actually, it wouldn't take as long to get the hot water.
Yeah. I mean, that's essentially what the swing tank is. If you think about it, it's a primary tank that's feeding a kind of a secondary tank that deals with the circ. And by having the pony tank, usually that'll decouple the flows between the boiler or the tankless water heater side or the heat pump and your loop side. But I think, when you say pony tank, I mean, functionally, it's there to support the reheating of the circ load.
I guess maybe I'm using the wrong words. I'm just thinking like actually in their unit.
Oh, in their unit. Got it. So this would be having a central system and then having another tank inside their unit. Now, would that tank have electric in it or just be storage in your?
I don't know. I just was curious if anybody's been thinking about that.
We had a project that was retrofit and it had a bunch of electric tanks in there. And so we had thought, oh, let's try this and just put all our storage in the units. And so that was trying to retrofit tanks and units with the central system and then having that extra buffer so that you didn't need it at the central plant. But it ended up being pretty hard to control and somewhat difficult compared to just doing it all centrally. So we moved away from that. But I think, again, trying to get your plant as central as possible is going to really reduce your loads. And that's really what we want to be trying to do here.
Okay.
Yep.
Thank you.
Yeah, thank you.
We've got another question here. Some areas within Seattle City Light Service Territory still experience 4 to 6 hour stretches of power outages. Climate change will make this worse. How does this central heat pump water system handle that?
So many of these power outages are predictable. I at least know in California, they're talking about grid resilience, right? So it's this idea that there's a big windstorm coming in. We can predict this. We want to shut down all these power lines so we're not causing forest fires or whatever. And so what they can do before that is charge up these systems, right? And so if you can, charge up for maybe 4 hours of load shift, then you can have that in storage to coast through this power outage.
And then I would just add that, in the Northwest, we do get the windstorms that happened. And, I mean, if we're out of power for a couple of days, I mean, you're not doing a whole lot, right? I mean, if you're out of power, everything's out. And, in that program, we're not making the hot water systems, stay on. I mean, if it's an electric building and the power goes out for 2 days, you're going to get what you get. I mean, unless the project installs some backup generator. But I mean, these systems aren't being deployed or touted as this answer to a grid that goes up or down. But if you do have more storage and you do have load shift, then in theory, you can kind of coast through a lot of these power outages. So if the power goes out for 4 hours and you've got a system that can load shift around and shift out the evening 4 hours, then you're gonna be fine because you're kind of loaded up around that. But yeah, I think we're not solving infinitely. We're not solving the power question or issue at the grid with these systems.
Shawn, thank you, Paul. I think that was the last of our questions. So I'm going to release everyone to networking. So if you want to jump to your speaker table, I'm sure people will join in and have some more questions for you.
Great. Well, thanks for having us.
Yeah, thank you.
Thank you.